So I'm going to repeat some material from last time just to remind you, right? So we were talking about, so today's lecture is, we'll basically talk about SVMs and duality. So we'll see that, we looked at the primal SVM problem last time, and today we will derive the dual SVM problem. And to actually solve for the coefficients, then in many cases, people actually have solved the dual SVM problem rather than the primal. Okay, so what do I mean by all this, right? So let me recap something that we talked about in the last 10 or 15 minutes of class last time. So let's consider a general constrained optimization problem. Okay, so the general problem we'll have is you want to minimize a function f naught x, okay? And then we have some inequality constraints on f, right? So fi x is less than equal to 0, I equals 1, 2 through m, okay? And then certain number of equality constraints. Okay, and we just always kind of assume that it is fi is less than, fix is less than equal to 0, right? If you had something which was greater than equal to 0, then you can just kind of, take negative of that and get a less than equal to inequality, okay? So this will denote, I think I might use it later, problem number 1. And last time we saw that we named it as the primal problem. Okay, because we started seeing dual last time. So again, here x belongs to Rn, okay, which means that my fi is a function from Rn to R, including f0, right? And so is hi, Rn to R. We said that we can actually form something called the Lagrangian, which is a function L that will basically take the primal variable, so it'll go from Rn, but it'll actually add some other variables which will be dual variables, or they will basically correspond to Lagrange multipliers that will essentially be the dual variables. So we will have dual variables for, or Lagrange multipliers for every inequality constraint and also for every equality constraint. So there are m inequality constraints. So Rm, p equality constraints, so Rp. And so this function takes maps Rn cross Rm cross Rp to the reals. In particular, we have these Lagrange multipliers lambda and nu. And my Lagrangian, this function is f naught x plus summation of I equals 1 through m lambda I fi x plus summation I equals 1 through p nu I hi x, okay? And lambda I is Lagrange multiplier for ith inequality constraint, okay? And mu I is Lagrange multiplier for the ith equality constraint. So that means that lambda I corresponds to hi, and nu I corresponds to, sorry, lambda I corresponds to fi, and nu I corresponds to hi, right? And like I said last time, the lambda and nu are also called dual variables. And then again, I'm repeating stuff from last time. We looked at this Lagrange dual function, which is basically just a function of the dual variables, right? So it's a function only of lambda and nu. Okay, and the way we do it is we take the Lagrangian and we take the infimum over x. Okay, so remember the Lagrangian, like I wrote above, is this function. So I'm just copying it below. F naught x, the summation of I equals 1 through m, lambda I fix plus I equals 1 through p, hix. And I'm taking the infimum over all x. And we will say that lambda and nu are dual feasible. Okay, so just to kind of the language that we are using is something called feasibility, right? So what would be a primal feasible solution? A primal feasible solution is basically feasibility means that it satisfies the constraints, right? So primal feasibility will just mean, so x will be primal feasible if fix is less than or equal to 0 for I equal to 1 through m, and hix is equal to 0 from I equal to 1 to p, but that x is not necessarily the minimizer of this problem, okay? So that's the language we are using. So x is primal feasible if these two sets of, m inequalities and p equalities are obeyed, right? And dual feasibility is if lambda is greater than or equal to 0, and it's just saying that, this has a finite solution. So it's not that this infimum goes to minus infinity, okay? And how many inequality constraints are these? Remember, this is a vector, and there are
M,
which corresponds to fi. So you're right that basically there are m inequality constraints, okay? And then last time we said, well, there are two facts that we should know about, which is that g of lambda mu is less than or equal to p star for any dual feasible lambda mu, which means that if you have any dual feasible lambda mu and I plug it in to this, then it'll be a lower bound for the primal solution. So P star, okay, so P star is primal optimal. Okay, that is optimal value of 1. Okay, so in particular, P star is equal to F naught X star, where X star is the solution to this problem. So X star will be primal feasible. It'll obey all these constraints. And in addition, it'll give the minimum value. Okay. So that kind of already gives us a hint that if you want to find P star, one alternate way could be to just look at the dual function, Lagrange dual function, and actually try to maximize it, right? Because it'll approach P star, okay? And fact 2 says, okay, basically that there are certain kinds of problems where if you maximize it, you will actually get the optimal solution of the primal and the dual. So if there exists a dual feasible lambda star, nu star, okay, and remember, this just means that lambda star is greater than or equal to 0, okay, and a primal feasible X star, such that G lambda star nu star equals P star is equal to F naught X star. So actually, this is only saying that, what are the conditions in which strong duality holds, right? Sorry, it's actually just saying what strong duality is, okay? So it's just saying that if I have my variables, primal variable X star, dual variable lambda star, nu star, such that all of them are feasible, X star being primal feasible, lambda star, nu star being dual feasible, right? Then strong dual, and that this value, G lambda star nu star, is not only at this lambda and nu, not only an inequality, but actually an equality. Okay? Then strong duality is said to hold. Okay, so far I've just reviewed material from last time. I did exactly the same thing last time. So now let's start with the new material. Okay, so we will now look at the dual problem, okay, which is I take my function, the dual function, okay, and I'm going to maximize this over lambda and nu. And the feasible region is where lambda is greater than or equal to 0. Okay, remember I could have written it as, lambda I is greater than or equal to 0, I equals 1, 2 through m. Okay, and this is just kind of encapsulating it. That I'm just saying that the vector of lambdas is greater than or equal to 0. Okay. So now let's look at what the consequence of strong duality is. Okay. And remember, I don't want you to lose the picture. We are finally going back to SVMs. And what we are going to do is going to allow us to interpret what the SVM solution actually looks like and give a faster way, potentially, of solving the support vector machine. Okay. So suppose strong duality holds for lambda star, nu star, and X star. Okay, so let's see what the consequence of that is. Okay, then let me write F naught X star. Okay, strong duality means that F naught X star is G of lambda star, nu star, right? That's exactly what strong duality is. So we are assuming that it holds. Okay, and from before, our definition of G of lambda nu star is that this is inf over X of L X lambda star nu star. Okay, so now we can substitute what L is. It is F naught X, the summation of I equals 1 to M. But remember, I'm doing it at lambda star. That's lambda I star fi x plus mu I star hi of x. Okay, since this is the infimum, right, then it must hold that this is less than equal to the value at x, any other value at x, in particular x star. Correct? This is the infimum over x. So this value, the infimum, will be less than equal to something else, right? And I can, at any other x, and I can substitute x star over here. So now I'm substituting x star in the above. Okay, so now we can kind of look at some quantities, right? This is dual feasible, right? So this means that this is greater than or equal to 0. Fi x star is less than or equal to 0. So this means that this quantity is less than 0. Similarly, I don't have any constraint on nu I, and you're actually seeing the reasons why, right? Because hix, remember x star is primal feasible, so this is equal to 0. And as a result, this whole quantity is equal to 0. So what I have over here is, I have f naught x star, and then something which lowers the value, something which is negative. So what that means is that this whole quantity is less than or equal to f naught x star. But what have I done? I have basically shown that f naught x star is, through a sequence of inequalities, is less than or equal to f naught x star. So what does that mean? That means that this is not just an less than equal to, but it's actually an equal to. This is an equality. And so must this be an equality. Okay? So the above two inequalities must hold with equality. Okay? So what does that imply? The first inequality says that x star must be actually a minimizer of this. So remember, that is a little bit subtle, right? So it's not, remember, x star was a solution to this constraint problem. Okay? From that, we derive, we went through the step of looking at the Lagrangian and Lagrange dual function, right? And it's basically saying that the Lagrangian, if I am at dual feasible, then this must be the minimizer. Okay, so x star must be the minimizer of Lx lambda star and nu star. And then the second part is that I must have an equality over here. But if you look at this, this is equal to 0, so that's fine. This, it says, and this is now actually really interesting. This is saying that this should actually hold with equality, not just an inequality. cannot be an inequality, strict inequality, right? So this means, and this will actually have very interesting implications for the SVM problem. So this says that summation of I equals 1 through m lambda I star fi x star equal to 0, right? And in particular, each of the quantities, because they all have the same sign, less than equal to 0, this means that lambda I star times f of x star must be equal to 0 for all I equals 1 through m. So for each of the inequalities, this must be true. Each of the inequalities fi. Remember that fi x star must be less than equal to 0. Okay, so what does this imply? And remember that primal feasibility is that this is greater than equal to 0. So this implies, so remember that lambda I star is greater than equal to 0. What if it is strictly greater than 0? So this says that if lambda I star is strictly greater than 0, then what happens?
And all the FIs have to be 0.
Then the corresponding fi, right? What do you mean by all?
You know, FI for the X star.
Yes, fi for the x star. So that's just, remember, that's just the ith linear inequality, right?
Right.
Right. So if the corresponding dual variable is non-zero, then this inequality must be met with equality. Similarly, there are two terms over here, right? So we've looked at the first one. Suppose this one is strictly less than 0. Then what must happen? The corresponding lambda must be equal to 0. Okay. So it basically says that, if this inequality has some slack, right, that means I end up having x star some such that fi x star is strictly less than 0. There's some slack in this inequality. And the corresponding Lagrange multiplier is actually exactly equal to 0. Okay. Again, right now we are looking at things in general, but it'll actually have implications when we start talking about going back to the SVMs and looking at the dual SVM problem. Okay.
So when you're talking about the corresponding, it means that like it could be that some of the lambda i's are 0 and some the other fi of X stars are 0, right?
Yeah, exactly. That's exactly what is going to happen. Right. It'll be not always true that all the things are going to be met with equality.
Right.
And we'll see that. We'll see that when we look at the SVM picture. Okay. Okay, so I'm actually kind of going to conclude and just tell you a little bit more about optimization or constrained optimization. So there is this very famous KKT conditions. Okay, this is called Karush-Kuhn Tucker, or short for KKT conditions. Okay, and they provide a certificate of optimality when problem 1 is convex. Okay, so what do I mean by problem 1 is convex? Well, I won't get too much into details, but it's F naught is convex, and these are all convex sets. Okay, which is true for the problem that we are interested in, which is the SVM. Okay, so the KKT conditions are as follows for X star, and so the primal variable and the dual variables. Okay. So one is, okay, what should happen? So if somebody presents X star, lambda star, nu star, okay, and somebody says, well, these are candidates for optimal solutions. X star, primal optimal, lambda star, nu star to be dual optimal. Well, the first thing is that they should satisfy feasibility, right? So they should be, X star should be primal feasible, okay? And lambda star should be dual feasible. And primal feasibility, remember, is Fi of X star is less than or equal to 0. I equals 1, 2 through M. Hi X star is equal to 0. I equals 1, 2 through P. And then dual feasibility is that lambda I star is greater than or equal to 0. I equals 1, 2 through M. Okay. And then this thing that we saw above, this quantity, this condition is called complementary slackness. Which is that lambda I star times f of I x star equals 0. I equals 1, 2. Okay. So this is the KKT condition for x star, lambda star, nu star. So if you give me x star, lambda star, nu star like this, then this is a certificate that X star is primal optimal, lambda star, mu star are dual optimal. And we've seen that this condition has two consequences that we saw above. Okay, so I'm trying to, so X star is a minimizer of L. So I'll just write this as X star equals arg min L X lambda star nu star. Okay. And what that kind of implies is, right, the problem is convex, that the gradient of L should be 0. F naught X star plus, and we'll be using this. Okay, so these are the KKT conditions. KKT conditions, X star, lambda star, and let's see if I can draw a box. Okay. So, this is very general and, we don't need to understand it in its full generality. So let's come back to the SVM problem. Okay, so let's come back to the SVM problem. It's actually quite neat. By looking at these conditions, how it'll lead us to understand what is actually happening in the SVM problem. Okay, so the SVM problem, remember, is minimize over W and W naught, half of W square, such that yi, so that means, all the points are classified correctly and with a margin, okay? W transpose xi plus W naught is greater than or equal to 1 for each of the points in the training data. Okay, so I can take this and write it in the form of f of I, right? So I can take, this is greater than or equal to 1. I want to make it, let me put it in standard form, right? And the standard form was that I have fi times of w to be less than or equal to 0. So I'm going to write it as 1 minus yi times w transpose xi plus w naught is less than or equal to 0. Okay? And then this becomes my f of w, f of I of w. Okay, so any questions about putting this in standard form? Okay, so when I say I'm putting this in standard form, I'm just writing it like this. Our variable that we are optimizing is w, right? So I have half of w squared as f naught, and I have fi's, and currently actually we don't have any equality constraints. Okay, so let's now churn the machinery that we've learned, right? So let's form the Lagrangian. The Lagrangian is a function of the primal variables, and then we have inequality constraints, and let me call the corresponding Lagrange multipliers or dual variables as alpha. So that's very much the standard way that people have looked at it. Okay, so that is, anybody wants to help me, or feel free to tell me what to write. Plus, for each of the inequality constraints, there are n of them. I have alpha I times FIW, right? Which is 1 minus YI W transpose XI plus W naught. Correct? This is my Lagrangian, right? And remember, from above, I can basically take the gradient with respect to the primal variable and set it to 0. Okay, so let's do that. So let me take the gradient with respect to W of L. Gradient with respect to W of, made the same mistake twice. L W W naught alpha. And remember that we have two variables, two W and W naught. Okay. So what is the gradient of this with respect to W? Well, it is just W. That's the gradient of half of W, 2 norm of W squared. Plus, if I now look at this, I have W over here. So I'll have plus summation of I equals 1 through n. I have alpha I. What do I have? Yi.
W transpose.
Well, remember, W is what I'm taking the gradient with respect to.
YI and XI.
It's xi, and there's a minus sign, right?
Yes.
This minus sign. Okay. And that I will set to 0. So look at the amazing thing that comes out, right? It's saying that W is actually at the optimal. It's actually going to be a linear combination of the xi's. And if you remember, we are using the encoding of yi is +1 for class 1, yi equal to -1 of class 2. And my dual variables, remember, are going to be greater than or equal to 0, right? So it's basically saying that you basically have some positive combination of xi's minus a positive combination of xi's. So a positive combination of xi's from class 1 minus a positive combination of xi's from class 2. Okay, that's what an optimal W will look like. And then if I now take the gradient with respect to W naught, well, look, W naught is not here. W naught is only here. So it's basically going to be summation alpha I, yi, W naught. And the gradient will be summation of, what's it going to be? I equals 1 through n
Alpha I
minus alpha I, yi.
with W, sorry.
That's it.
Yeah, that's it.
Equal to 0. So that means that you actually have a little balancing constraint, which means that the alpha i's, the summation of the alpha i's from class 1 are actually equal to the summation of alpha i's from the other class. Because yi is +1, okay, for class 1, and -1 for class 2. Okay, so let's look at the dual now. Let's try to derive the dual, right? So the dual function, remember, we only have one set of dual variables now, right? Because we don't have any equality constraints. So I have that g of alpha is my dual function, and that is the minimizer w naught L w naught alpha. Okay, and we saw that the minimizer will actually have this property. Okay, so I'll have g of alpha, okay, is going to be equal to half of, so remember, this is my L. I found that the minimizer is this. So I'm going to substitute this W over here and this W over here. And we'll also see that we'll need this. We'll be able to use this condition. Okay. So this means that my W is of the form I equals 1 through n, alpha I, yi, xi. Okay. So this is half W squared, correct? And now I have this. Let me write this as well. I have a term which is just alpha I from here, alpha I times 1. And then I have minus summation of alpha I, yi, xi transpose times W, right? And W is alpha I, yi, xi. So any questions? Okay. I just wrote W transpose xi as xi transpose W. It's the same thing, right? And then I just substituted this over here. Okay, and I think there's one more term left, which is alpha I times W naught, right?
Right.
Alpha I, Y I times W naught, okay? It's plus summation of alpha I, YI, and W naught. Or maybe we can look at this term, right? What is this value?
0.
0, because W naught is some one particular value, doesn't depend upon I. Okay, so this term is 0. Okay, and that follows from here. Okay, now look at the rest part. So let's let me write G of alpha. Let me first take this term, summation of I equals 1 through n alpha I. And now if you look at this is half of this square. And if you closely look at this, I made a little, I don't want to use the same I over here and the same I over here. So I should have used J over here. Okay. So basically I have all the possible pairs, alpha I, alpha J, YI, YJ, XI transpose XJ. And if you expand this out, that's exactly what you would get. But they don't exactly cancel because there's a half over here and 1 over here. So as a result, these two terms combine to give you minus 1/2 summation of I equals 1 through n, summation of J equals 1 through n, alpha I, alpha J, YI, YJ, XI transpose XJ. Okay, as a result, here is the SVM dual. So we've eliminated W and W naught, and we now have an optimization problem only in the alphas, and we want to try and maximize the dual. So I maximize over alpha, summation of alpha I equals 1 through n, minus half. I'm just copying what I have above. I equals 1 through n, J equals 1 through n, alpha I, alpha J, YI, YJ, XI transpose XJ. Such that, remember, I have dual feasibility. Alpha I is greater than or equal to 0. I equals 1, 2 through n. And actually, it turns out that in this case, I do have one equality constraint, which comes from here. Okay, which comes from here, which is that summation of alpha I, YI equals 0. So this is my dual problem. Now, this might be a good time to stop to ask for questions. So remember, what we've shown is, maybe I'll try to fit this on the same slide for a minute or so. Okay. So this was my primal problem. And what I've shown using the theory of duality is that this is equivalent to solving this. But note that here, the primal variables are W and W naught. And here, there are these more abstract things, which are alphas. Okay, but I can solve for this, and it turns out that this problem is actually a little bit simpler to solve. It has these inequality constraints, which are kind of non-negative constraints, just one equality constraint, whereas these inequality constraints can be a little hairy. So most solvers for SVM problems actually use this. Questions?
Sorry. What happened to the first term in the original G of alpha?
Which term, sorry?
One half. Yeah, that one. Yeah, sorry.
So what I showed is, so if you expand this out, right? So let me just actually, okay. I'm just going to use kind of a little scratch work, right? So alpha I, sorry, what do I have? Yeah, I have this, right? Alpha I. Okay, so remember that this is the two norm, right? So I have, this is alpha I, yi, xi transpose times summation of j equals 1 to n, alpha I, alpha j, yj, xj. Is that clear? That's just saying that norm of y square, norm of z square is equal to z transpose z. That's all I've done. Is that clear?
Yeah, that makes sense.
Yeah, if that's clear, then the next step should not be too difficult. It's basically just I equals to 1 through n, alpha I, alpha j, yi, yj, xi transpose xj. Correct? If I expand this out.
Yeah.
So half of this will be half of this, which is half of this. And what has happened is that there's a half over here, there's a minus 1 over here. So that combines to give minus half over here.
I see. Okay. Yeah, that makes sense.
Yeah? Okay,
Yeah.
great. Thanks for the question. Do you want me to leave this on my notes or?
Oh, yeah.
I'll just leave this. I won't erase it. I'll just say note that okay. Any more questions on this?
I don't understand how we arrive at alpha.
How we arrive at alpha. Okay, so just think about alphas as Lagrange multiplier for each of these, right? So there are n inequality constraints. The alphas are basically like the lambdas before. They correspond to the inequality constraints. So I'm basically doing alpha I, fi, w. And this is the fi. So I form these are the Lagrange multipliers. I get a dual. And then I do this.
Oh, so we just take like we just take like the derivative and solve for alpha, right?
So remember, right. So I basically, I did go over, right, that in general, we have this. Okay. And in the end, what I showed is that when you have this must be true. Okay. Which means that when I take my Lagrangian, then I can basically set this equal to 0 with respect to the primal variable, the gradient with respect to x. So that's what I did over here. That I took the gradient with respect to w and I set it to 0. And then I get w in this form. So this way I'm eliminating the w and w naught from the dual dual function, which is what I need to do. And that's how I get a function just in terms of the alphas.
All right, that makes sense. Thank you.
Okay. I mean, it's kind of amazing, right? I mean, if you just look at these problems, and if you ask, a random person on the street to say, well, is this problem the same as this problem? Right?
Yeah.
Chances are they'd say no.
Yes, actually, what I was wondering is that what was the initial motivation? Like, someone get into this and then somehow get out the other side of the equation and then, realize this, or,
Yeah, I mean, you have to realize that, if you think about deep learning and so on, right, it's been really the wave in the last, I want to say 10 years, right? There was a time when SVMs, they started finding that they actually gave very high quality solutions, right? So there was a period of about 15 years in which people did a lot of work on SVMs, and I would say that there were thousands of papers published in this area. And one of the first things that they realized is that, you wanted to solve this problem, right? For not this problem, but this problem for very large data sets where N is very large. And they realized that solving this was a little bit much harder, whereas solving this was actually much easier. Okay. And you have to realize that, there's a whole branch of applied mathematics on optimization theory. It's very well developed. And so this was kind of his classical optimization theory applied to this machine learning problem.
But there was a time that people were actually trying to solve this, and then it developed that,
Yeah.
Lagrangian and that dual problem, and this is a
Yeah.
problem to solve, right?
Yeah. Look, I mean, if you showed this problem to somebody who's an expert in optimization, they would do this right away. Right. So it's not like it was pulled out of a hat or something, right? But if one knows optimization theory, then one would go from here to what I just showed you. So it's not that surprising that people were able to find this. All I'm saying is that, if you just look on the surface and look at the problem, and I just said random person on the street, right? Not an expert in optimization, right?
Right.
They would basically say that these problems, they don't really look anything like each other. Okay.
Thank you.
Wait, how do you derive the weights of W from alpha? Because all we know is that G of alpha equals F of W star, right?
Remember this part in the middle, right? So W, given the alphas, you can find out W's.
I see. Okay.
Right? And it's alpha star, alpha, the solution of the optimal, suppose the solution of here is alpha star, then it'll be alpha I star, yi, xi. And that's the beauty, right? It actually gives you an interpretation that this solution is, basically a linear combination of the xi's, and it'll turn out that these xi's are actually special. We'll look at complementary slackness in a little bit and see what alpha i's are actually greater than equals to. So by solving the dual problem, you will get the separating hyperplane explicit.
So,
Okay.
so
Any more questions?
is it always the case that when solving when setting the Lagrangian equal to 0, you'll get a closed form expression of the primal variable in terms of the dual?
No, I mean, we are looking at a very, very specific quadratic problem. In some sense, it's actually kind of an easy optimization problem.
Got it.
Okay. Okay. But actually, I just also want people to know is that, even though the optimization people, obviously for them, it's easy to know, but the actual methods that came up to solve these problems were very much, it wasn't obvious how to solve this problem to them very fast for very, very large data sets. And it's the machine learning people who kind of did that. And in a way, it actually led to these fast methods like SGD and coordinate descent and so on, which then later paved the way for deep learning. Right? So kind of there's a kind of a chain of things that has happened. And it's the work in this area ended up being very valuable for the current work. And who knows what will happen in the future, and that's why we kind of teach the basics in this class. Okay, so let's move on. So we saw something called complementary slackness, right? Okay, so complementary slackness, what did it say? It said that at optimality, the alpha I, so I'm not going to put the stars over here. Alpha I W naught must satisfy this Lagrange multiplier times f of Fi W star, right, which is 1 minus Yi W transpose Xi plus W naught equals 0 for all I. Okay, that's exactly the complementary slackness condition over here. Where was it? This one. The Lagrange multiplier times the inequality constraint must be equal to 0, and just I'm not writing the W star. That's all. The stars over here. But these are optimal solutions. Okay, what does this mean? Okay, so remember, it means that if alpha I is greater than 0, then Yi W transpose Xi plus W naught must be equal to 1, which means that this quantity must be equal to 0. And if Yi, actually, I don't think I need this initial brackets. If Yi times W transpose Xi plus W naught is greater than 1, then alpha I should be equal to 0. Okay, so this is just algebra, right? But now let's come back to our two-class problem, right? We have two classes, okay? The pluses and the second class, the minuses, right? And remember, we said that this is our hyperplane. This is W, and this is the margin. And we are trying to maximize the margin. Okay, maybe instead of minuses, I'll just, because it gets confused with the dotted lines. There are some pluses over here. Okay, so now let's look at this condition, right? If Yi W transpose Xi plus, so this means that this Xi is actually right on the margin. It's right here. Okay, so let me write this in red. Yi W transpose Xi plus W naught equals 1. And this xi is basically these xi's. Because it's met with equality. So that means that these actually lie on the margin, right? So that means if the W alpha I is greater than 0, that means these points are on the margin.
O's on the dotted line, right?
And similarly, the O's, yeah. Sorry, is that what you were saying, Thomas?
Yes, yes. Because then yi is
Yeah.
1 and then
And
these.
remember, what is my W? Is equal to summation of alpha I. Actually, let me just write it below. Actually, I already wrote it, sorry. So W is equal to summation of alpha I, yi, psi. And this condition, what it is saying is this condition, okay? I don't need to maybe write the whole thing in green, but xi, this means that they don't lie on the margin. And if they don't lie on the margin, it means what?
Alpha I for them is equal to 0.
Alpha I equals 0. Oh, sorry. Yes, alpha I equals 0, right? And here it was that sorry, the picture is getting muddled, but alpha I is greater than 0. Okay. But you can say that, from here, W is linear combination. This is at optimality, right? Of support vectors. Okay, and the support vectors are the ones that are kind of like supporting the hyperplane, right? That's why they're called support vectors. So these are alpha I is greater than 0. So you kind of get this really beautiful interpretation. That the separating hyperplane, the optimal separating hyperplane, is actually just a linear combination of the support vectors, where the alphas are actually greater than 0. So one of the reasons why, SVMs were so important is because, you don't really necessarily in classification, you don't really care about what this looks like. You just want to separate the, one class from the other. And that's what the support vector machines are doing. You're not trying to model this as a, multivariate Gaussian. You don't really care what this is, what distribution this comes from. All you're trying to do is separate the two, right? And support vector machines were, one of the best performing methods for doing classification till deep learning came along. And the reason why deep learning is much, much better is actually different, right? It basically allows you to have lots and lots of parameters and optimize over that. Okay. Any questions? And see, we could only arrive at this by understanding the duality, right? Otherwise, you would not be able to get this. There's a very important issue so far that we haven't talked about, which is that we've kind of assumed that the problem is linearly separable, right? But in practice, you can have outliers, you can have noise, or the problem might not be linearly separable. So for it to be a viable method, right, you need this to be applicable to non-linearly separable data. Okay. So I'm very quickly going to give you the idea behind non-linearly separable data, right? So recall the original separable. So right now I'm going to say that, this problem, then remember this was also a drawback of the perceptron, right? In the perceptron, it was not clear how to modify the problem, but it turns out that for the SVM, we actually have a very good modification, which in practice works really well. So the initial thing that we did when we started talking about maximizing the margin, right? We said we want to try to maximize C, which was the margin, such that each point, the margin of each point would be greater than or equal to C times norm of W, right? And what we are going to do is that instead of, so this basically says that the points are separated by a margin, right? So this basically says that the points have to be linearly separable, okay? In order to extend this to non-linearly separable data, so in order to allow non-separable data sets, what we will do is we will relax the above inequality to have a slack. So what do I mean? We will change the inequality such that I have same thing on the left-hand side, right? Because that's just talking about, whether the problem is correctly classified or not. But I will actually have C, and then we will introduce theta I times norm of W. And this is going to be greater than or equal to 0. Okay, and you can see that psi I is greater than or equal to 0, right? So suppose that it is 0, then you get back the problem. Now suppose you start increasing it, suppose you make it 1, that just means that it is correctly classified. And then as you make it bigger than 1, then we actually assume that some points could be incorrectly classified by the hyperplane. Okay? So here is the, if I now, make this change, then same as before, same as earlier. Okay, we can fix C times norm of W to be equal to 1. And then I get, now I'm going to not go into like a lot of details, but non-linearly separable SVM will have the form, which is you take the primal, you take W naught psi, you take half norm W square. So this remains the same, half the objective, but now you have 3 variables, 3 sets, W naught psi, and you have yi times W transpose xi plus W naught is greater than or equal to, instead of 1, you get 1 minus psi I equals 1 to n. And then you basically, remember that psi I is greater than or equal to 0. And what you can do is you can say that, I want to control how much, remember the larger the psi I is, that means the, more uncertain in some sense, it starts lying on the wrong side of the hyperplane, right? When psi I is greater than or equal to 1. So you want to limit the size of the psi i's. So one way to do it is you say that the summation of psi i's is less than or equal to a constant. And what then one can do typically is you can take this and you can put it over here. Okay. So that's kind of like trying to derive it, right? But if I had to give the final SVM primal, it would be minimize half norm of W square plus the gamma parameter summation of psi I. Okay, and then the constraints I have, again, I'll write it as a linear inequality constraint, 1 minus I minus yi W transpose xi plus W naught is less than equal to 0 for I equals 1 through n. And we have introduced these extra variables. So psi I is greater than equal to 0. Okay, and if you want to treat the corresponding inequality constraints, you would basically have that minus psi I is less than equal to 0. Okay, so this is the non-linearly separable, which is how it should be. Okay, because in the beginning, you won't know whether the problem is linearly separable or not. So the SVM problem is basically this one. I did not want to introduce the full generality of the problem right in the beginning. Okay, it's exactly this. Okay, and the corresponding dual, again for non-linearly separable. The corresponding dual is you basically chug through the same machinery that I did before, right? And what you end up getting is you get maximize over alpha. Very similar, summation of alpha I equals 1 through n, minus 1/2, summation of I equals 1 to n, summation of j equals 1 through n, alpha I, alpha j, xi transpose xj. No change so far in the F naught or alpha I is greater than equal to 0. Summation of alpha I yi equals 0. So far, this is the same as this linearly separable SVM. But it turns out kind of really interesting that if I apply the machinery over here and look at, the dual problem, then all I get is that this is less than equal to gamma. Okay, so as exercise, you can do the following, which is derive the above SVM dual. So I would encourage you to do it, okay, which is, from here, apply the different steps that we had, right? Form the Lagrangian, form the gradient with respect to W and with psi this time. So that's going to be the new thing. So I think I made a mistake over here. And this is the slide. Do that, okay, and then substitute it in the dual function, and this is what you will get. Okay. So that concludes this lecture. Is probably the most mathematical of all the lectures that I will give. But I just thought that it would be interesting for you to see how you can use optimization theory to actually get pretty good insights in the machine learning aspects, right? The fact that these vectors only are linear combination of the support vectors that lie on the margin is quite interesting, right? Otherwise, you would not have thought. And then in many courses in machine learning, you'll hear people talk about support vector machines. They'll just talk, this blob of points, this blob of points, and the hyperplane. And that's what people end up getting. But I think it's really valuable for you at least once in your life to see that this can actually be derived from optimization viewpoint. And we've actually only spent 2 lectures on it, right? It's not like we've spent lots and lots of lectures on this. Okay. I'm a couple of minutes over, but any questions?
Thank you. That was very interesting.
Yeah, it is. Yeah, I mean, that's why I like to teach it because I just find this super interesting. And just one thing I would like to also remind you, right, that you might say, oh, in the era of deep learning, who needs all this, right? But you don't know where the era of deep learning is going, right? It could be that many of the insights that you gain from here can actually be used to make your deep learning methods either better, or you can understand them better, or who knows what will happen in the future also. Okay.